Yes, welcome to video session. Let us learn something new today. And before going to the today's topic, let us recall what we have learned in the previous class. From video 1, we have learned what actually our subject is, that is strength of materials. And we came across the different definitions like a force. And also we have understood the concept of stress, different types of stress. And also we have understood the concept of strain along with the different types of strains. Now, in this slide, now let us study one important topic, that is Poisson's ratio. Poisson's ratio. So it is represented with the help of a symbol mu. So with the definition, we can understand it as it's a ratio of lateral strain to linear strain. So you may get question what actually the lateral strain and the linear strain is. Once you are thorough with the different types of strain, then you can clearly understand what actually the lateral strain and the linear strain is. So to understand the concept, once again, I'll explain in brief what actually the lateral strain and linear strain is. For this, I'll take an example, a cylindrical rod of length L and a diameter D. I'll apply load on both the sides. In this case, I am applying tensile load of magnitude P. If I apply a load on both the sides, definitely there will be certain changes in shape and size. So we get the final shape that is represented with the help of a dotted line. Once we get the final shape, let us measure the length and the diameter of the final shape. First, I'll measure the length of a final shape. It is represented with the help of a L plus delta L with the dotted line arrow marks. So the original length is L, the final length is L plus delta L, and it's clearly understood that there is certain changes in length. The same change in length is represented with the help of orange color arrow marks indicated with the delta. In the same way, on clear observation, it is very clear that diameter is also changed. It is represented with the help of a green color arrow marks indicated by delta. Students, here I am applying a tensile load. So there is a changes in two dimensions. It's very important. There are changes in two dimensions. The first dimension is the length and the second is diameter. If I take length as a reference, then it becomes a longitudinal strain or linear strain. If I take diameter as the reference, then it becomes lateral strain. Very simple. So the formula becomes, for Poisson's ratio, the formula is mu is equals to EL by E, where EL is lateral strain, E is longitudinal or linear strain. So this is a concept of Poisson's ratio. And normally the Poisson's ratio will not exceed 1. This is a constant value. It has got some value in between 0 and 1. Sometimes we can say it is minus 0.3 to 0.5 or up to 1. It doesn't exceed 1. Now, in this slide, let us study the stress strain curve. For this, I'll take an example of a ductile materials, out of which I'll be taking mild steel as an example. Normally, there are ductile materials and brittle materials. In the next slide, in the next concept, I'll deal with the brittle materials. This is the stress strain diagram for mild steel, where stress is plotted on y-axis and strain is plotted on x-axis, and this is the curve where a b c d, these are the parameters, and I'll explain in detail what actually these parameters are. Before understanding this curve, first we need to understand how we got this curve. Just to understand this, so we need to observe this one. This is a slide. This is an animated picture where it's very simple. This is very important one. See here in the middle, this is the workpiece. I'll take mild steel as an example. So I am applying a tensile load on both the sides. In this case, I'm applying tensile load on top and below. So this animation shows it's a clearly it shows I am slowly applying the load, and there are certain changes in the dimensions of a bar. This rectangular rod, sorry, this circular rod. Simultaneously, here the graph is getting plotted. So this graph is stress strain curve for this material. So this is how we get this curve. So it's very important. So just observe the changes. Just observe the changes in the curve and as well as in the material. So let's look into the stress strain curve point wise, where A is called proportionality limit. A is a proportionality limit. This point is called as a proportionality limit, and B is called as elastic limit. C is upper yield point. D is lower yield point. Together we call it as a yielding. And E is nothing but ultimate point. F is nothing but fracture point. First, let us understand what actually the proportionality limit is. As the name itself says, proportional. That is nothing but stress is proportional to strain. Stress is proportional to strain up to point A. From origin to point A, stress is proportional to strain. So it's a value of a stress up to which stress is directly proportional to strain. So now it's coming to the elastic point. What elastic point says? It's a value of a stress in which object is elastic in nature. Students, it's very important. This is a point B. This is an elastic point. If I draw a line vertically, this is a line. I am drawing a rough line. This is a rough line. The area from origin to elastic point is elastic region. This entire thing is a elastic region, because within elastic limit the object behaves elastically. I mean, before point B the material is elastic in nature. Once it crosses the elastic limit, then it enters into the plastic range. Understood? So now let's understand yield point. So point C and D, point C is called as upper yield point, point D is called as a lower yield point. In between, there is a process called yielding. In this yielding, for very small changes in load, there is a major expansion, there is a major extension in length, there is major extension. This is what happens in the yield point. It's a point where there is a large expansion for very small changes in load. Now coming to the point E, this is the ultimate point. Ultimate point is nothing but a maximum load carrying capacity is called as a ultimate point. Each and every material has its own value up to which it can withstand the maximum load. That value is called as a ultimate point or ultimate stress. Next, fracture point. Fracture point is a point where the material breaks. It's a value at which the material breaks into pieces. These are the different parameters. It's very important to understand and remember the order of these points. That is, one first is proportional limit, then elastic limit, upper yield point, lower yield point, ultimate point, then fracture point. Students, and there are many parameters that come in a stress strain diagram. As I said, this is the elastic range. So students, as I said, this is the elastic range. And one thing I'll draw, see, this is Yes. From D to E, from D to E. So here, this is called as a strain hardening or work hardening takes place. Here, the strain hardening or work hardening takes place. In this region, the strain hardening or work hardening takes place in this region. This is very important. In this region, the strain hardening takes place, strain hardening or work hardening. Whereas in this case, in this from in between E and F, it is necking, necking, necking takes place. In the region E and F. In the region, it's E and F, it takes place, necking takes place. It's a necking. Okay, it's one of the very important parameter here. As I said, this is the elastic region. This is the elastic region. Here it is a elastic region. Elastic in nature. This one elastic in elastic region. Whereas the next point is plastic. This entire thing after elastic limit until the fracture, it is a plastic range. I think it's clear. Okay, now let's move on to the next slide. Yes. So this is initially I showed this slide. The way we got this strain curve, you can clearly understand this is a proportionality limit and this is a yield stress that's in between upper yield point and lower yield point. This is the ultimate stress and this is a fracture stress. Students, just for a while I'll show this slide. Just observe simultaneously both this testing one and also plotting curve. Just hardening has take place, strain hardening or work hardening. Now necking will take place, then fracture, it's very simple. So this is what I have shown in the previous slide. See this elastic region, once it crosses the elastic region, it goes to the yielding. Yes, it is yielding. After getting the yielding, it goes hardening, then ultimate stress, it reaches ultimate stress. Yes, ultimate, then necking, then finally it's break into two pieces. This is what the stress strain diagram for ductile materials. Okay. Now, now let us plot a stress strain diagram for brittle materials. So this is a stress strain diagram for brittle materials. It's completely different with slightly different with the ductile materials. In the same way, here also stress is plotted on y-axis, strain is plotted on x-axis. This is a curve. And here you can see is a point y. Point y is nothing but a yield point, and this point is nothing but a ultimate point, and it is a fracture point. It is a fracture point. So here this is the elastic range, elastic region, and this is a strain hardening. This is a stress strain diagram for brittle materials. Now let us compare elastic stress strain diagram for ductile materials and brittle materials. I will plot side by side. This is a stress strain diagram for ductile materials. It is slightly different what I showed in the previous slide, but the concept is same. So what's the difference? Just observe, clearly observe, you can identify the difference. What's the difference? The major difference is brittle materials does not undergo yielding. If they undergo yielding, it's very minute, very minute yielding. This is a first difference between ductile and brittle materials. Ductile materials will undergo, definitely they'll undergo yielding. Whereas in case of brittle materials, they will undergo very negligible yielding. And in case of ductile materials, there is a word called necking. There is a process called as a necking. Whereas in case of brittle materials, there is no necking, because necking takes place in between ultimate point and fracture point. In case of brittle materials, ultimate point is itself a fracture point. So there is no process called necking. It's one of the very important difference. Ductile materials have necking, whereas brittle materials doesn't undergo necking. This is a very important difference between ductile and brittle materials. Okay. Now let's move to the next slide. After understanding in detail of a stress strain diagram, it's a important topic to understand is a factor of safety. We have two materials, ductile materials and brittle materials. So we have different definitions for factor of safety for ductile as well as a brittle material. So as I said, there are two materials. First, let us understand for ductile materials, it is defined as a ratio of yield stress to the working stress. Since ductile materials will undergo yielding, so yield stress has taken as a reference. And working stress is nothing but a design stress. Sometimes we call working stress a design stress, sometimes allowable stress, permissible stress, safe stress. It has got different names. So FOS, factor of safety, is nothing but yield stress divided by working stress. Whereas in case of brittle materials, it's a ratio of ultimate stress to working stress. In case of brittle materials, there is a negligible yielding. So that is why we will take ultimate stress as a reference. Ultimate stress divided by working stress. FOS is equals to ultimate stress divided by working stress. And it's very important thing, students, it is to be important thing to be noted that working stress, allowable stress, permissible stress, safe stress, design stress, both are same. Both are all are same. So there is no need to get confused. Okay. So this is about the factor of safety. Now let's deal with the engineering constants. So mainly there are three engineering constants. One is Young's modulus. Next is bulk modulus. Next, modulus of rigidity. Young's modulus is denoted with the symbol capital E, bulk modulus with capital K, modulus of rigidity with capital G. Young's modulus is defined as ratio of stress divided to the strain, and with the formula capital E is equals to F by E, where F is stress, small e is strain. First, we need to understand the way we got this formula. Is the Newton per mm square is the unit for Young's modulus. So from Hooke's law, what Hooke's law says? Hooke's law says up to elastic limit, stress is directly proportional to strain. Students, it's very important. What Hooke's law says? Hooke's law states that up to elastic limit, stress is directly proportional to strain. So this is what we can write it as a up to elastic limit, stress is directly proportional to strain. F is directly proportional to E. If I want to remove this proportionality limit, if I want to replace with equal symbol, then I need to put one constant value. That constant I use is Young's modulus, that is capital E. Then the formula becomes F is equals to capital E into small e, that is Young's modulus into strain. On cross multiplication, I get capital E is equals to F by E. So this is how we got this formula. E is equals to F by E. Okay. Now let's move on to the bulk modulus. It is defined as a ratio of a direct stress to volumetric strain, where K is equals to F by EV, where F is nothing but direct stress, EV is nothing but volumetric strain. Next, modulus of rigidity, ratio of a shear stress to shear strain. So G is nothing but modulus of rigidity, Fs is nothing but shear stress, Es is nothing but shear strain, where Newton per mm square is the SI units for engineering constants, that is Young's modulus, bulk modulus, and modulus of rigidity. This is the concept of engineering constants. Once I study the about engineering constants, It's very important to relate among the engineering constants. So this is what the topic is. Relationship between engineering constants, that is E, K and G. First, let us understand the relation between E and G. The formula is E is equals to 2G into 1 plus mu, where E is equals to Young's modulus, G is nothing but modulus of rigidity. What is mu? Mu is nothing but Poisson's ratio. And the next relation is a relationship between Young's modulus and bulk modulus. The formula is E is equals to 3K into 1 minus 2 mu, where E is Young's modulus, K is bulk modulus, mu is nothing but Poisson's ratio. Then relationship between EKG, the relation between three constants. It is written as E is equals to 9kg divided by 3k plus g, where E is Young's modulus, K is bulk modulus, G is modulus of rigidity. Very simple. These three formulas are very, very important while solving the problems, especially very important while solving the problems. Students, this is what the slide which shows the formulas used. The formulas used. Students, this is what the formulas used. So these are the important formulas that we come across while solving the problems. Just I'll recall the formulas. Just I'll read out the formulas. The area, A is nothing but area. The formula is pi by 4 into d square. For circular cross section, if it is a rectangular cross section, then the formula becomes area is equals to, if it is a rectangular cross section, the formula becomes A is equals to B into T, breadth into thickness. B into T will be the formula. B into T will be the formula. Okay. For stress, F is nothing but a stress. P by A is a formula. F equals to P by A. Longitudinal strain E is equals to delta L by L. As I clearly mentioned, while taking a longitudinal, the length should be the reference. If I take length as a reference, then it is a longitudinal strain. For lateral strain, I should take other than length as a reference. If it is a diameter, then diameter should be taken as a reference. If it is thickness, breadth is taken as a reference. Okay. For lateral strain, EL is equals to delta D by D or delta B by B or delta T by T. This is a very important formula for lateral strain. And Young's modulus is equals to E equals to F by E. And this is what the factor of safety for ductile materials. Fy by Y. Fy is nothing. F is nothing but stress. Y is nothing but yield. Fy is nothing but yield stress. And this is a stress, safe stress. Factor of safety for brittle materials, ultimate stress divided by safe stress. And this is a engineering constants, relationship between engineering constants. E equals to 2g into 1 plus mu, E equals to 3k into 1 minus 2 mu, E equals to 9kg by 3k plus g. Okay, students, this is the formulas used. In this slide, in the next slide, let us understand about unit conversions. When one of the very important concept, that is unit conversion. In the next class, I'll be dealing with the unit conversions.